Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 11, the most important property of logarithms. Okay, so we're getting into a property here and we're going to use what we learned from lesson 10, and I brought that in. It is the formula or the equation that states that the log of 10 to some power times x equals k plus the log of just x. So what happens is the power goes out in front and you add it to whatever the log of the x is. And we're going to practice that here. So they gave us a table below. They calculated the log of 1 through 9 and gave us these decimal values. Now notice that would be 10 to the 0, which is 1 times that number, which just gives us these numbers. So if the power is 0, think of it as the log of 10 to the 0 times x equals, well, my k is 0 here, so it'd be 0 plus the log of that x. So this is the log of 1. This is the log of 2. So that's 10 times 0, or just simply the log. So we're going to add to that now, and we're going to find the log of 80. So I'm just going to show this one time. Well, no, I guess the log of 80. Let's just show our work. The log of 80 equals the log of 10 to the first power times 8. Okay, 8 times 10 to the 1 is 10. 8 times 10 is 80. These two are equivalent. So our rule now states that that's going to equal the power goes out in front plus the log of 8. Okay. So then I come up to my table and I see that the log of 8 is 0.9031. So therefore that is going to equal 1 plus 0.9031. And therefore the log of 80 is 1.9031. Okay. Now, once you get the hang of this, it's actually quite quick. So now I would just need to do the log of 7. And I have 3 zeros, so that's power of 3. But I'm going to show all my work just for practice purposes. So the log, let's change the color. The log of 7,000 will equal the log of 10 to the third power is 1,000 times 7. Well, that's going to equal 3 plus, the power goes out in front and added, 3 plus log 7. So that's going to give us 3 plus, and I'll just add it to this decimal since I'll just skip this step. So it's going to be 3 point, the log of 7 is 8451. Okay, so this is a really important property. And I'm using equal signs, and I should be using approximations. So approximation, because logs are usually irrational. All right, so let's try the next one. This is going to equal the log of 10 to some power times 6. Well, if I'm going the other way, that's going to be negative, and it's 1, 2, 3, 4, 5 places. So this is going to be negative 5. So the log of 10 to the negative 5 times 6 is going to equal negative 5 plus the log of 6. Okay, and so that is going to give us an approximation. Now we need to be careful when we're doing negatives. The log of 6 is 0.7782. My answer is not going to have that in there. Think of 1,000, or actually, let me do it this way. Think of it this way. 1.0000 minus 0.7782 is going to give us 9, not 9, 0. This will be a 9. This will be a 9. This will be a 9. 10 minus 2 is 8. 1, 2, 2.0. That's going to give us 0.2281. All right, so with negatives, we actually have to find the complement that gets us to a whole number, if that makes sense. So -5 plus log 6, which is this, will give us a negative 4.2218. All right. Okay, so be careful with the negatives. All right, part D. The log of 3 times 10 to the 27th is going to equal. So this is already done for us. I could rearrange this and say the log of 10 to the 27. Actually, that's times, so it's not plus. This is going to, no, that's right. So this is times 3. So I'm just rearranging these, putting them in the opposite order. So it's 10 to the 27 times 3. And we are already in our formula, the form of what our formula takes. So the power goes out in front, and you say plus the log of, that's a multiplication symbol, by the way, not a 0.3, the log of 3. So that is going to be an approximation of 27 point, and I go up to my 3, and it's 4771. All right. Part E. For an integer k, so they made this in general, we're going to come up with a rule now. So I have the log of 9.0. I'm going to rewrite this as the log of 10 to the k times 9. And that is going to equal k plus the log of 9. And that's going to be an approximation of k 0.9542. If k is positive. Oh, so if k is positive, it will give me this. If k was negative, all right, so I suppose I should just leave it at this point right here. Let me put a box around that. So this would be our answer. Because it says for an integer k. Well, if k is a positive integer, I would get this. But if k were negative, so I'll say for negative k, it would be a negative k point, and what number will give me 1 here? So what plus 2 gives me 10? That's 8. Carry the 1, 5. Carry the 1, 4. Carry the 1, 0. Okay. So if it were negative, it would come out to be a negative k 0.0458. Make sense? Hopefully. Okay, page 2 brings us to the exercises. So pause the video, see if you can do these without watching this first, and then come back and watch the video and check your solutions. So it says to use your calculator to complete the following table. So let me open my calculator up and share. All right, so here we go. It says round to 4 decimal places. So the log button is right there, and I want the log of 10, and it's 1. Round to 4 decimal places. Let me highlight that. Round to 4 decimal places. So I got 1.1234. Log 12. Enter. 1.0792. Don't forget to round that 4. So you have to look at the 5th position. If it's 5 or greater, this gets 1 more. All right, 16. Log 16. 1.2041, 18, log 18, 1.2553. And just to save time, we all know how to hit the log button. This will be 1.3010. This will be 1.3979. Log of 30 is 1.4771. Log of 36 is 1.5563. And the log of 100 is 2.12340. How do I know that's 2? It's 10 squared, power of 2. That's the log. All right. So number 2 says to calculate the following values, do they appear anywhere on your table? So I'm going to do the log of 2. And now I need to close my parentheses because I'm not done with my command. Plus log 4, enter. And I got 0.9030. So then it's asking if we see that anywhere on our tables. Let me switch to 0.9030. Do I see 9030? No, I see 90308 is 9031. That is right here. Okay. So I'm going to mark this with yellow. I'm going to show something to you. We're going to keep track of what's going on here. So the log of 2 plus the log of 4 is an approximation of 0.9031, and that is right there. Number 2, log 2 plus log 6, enter. And we got an approximation of 1.0792. Okay. Change to green. 1.0792 is right here. So B matches 12. Okay. Hopefully you're putting 2 and 2 together here. We're leading up to something. D log of 3 plus D log of 4 equals an approximation of 1.0792 again. Well, that's the green one. So let's go back to my highlighter. This matches this. So that gets a green mark. Let me go back to my pen. Log of 6 plus log of 6. Log 6 plus log 6 gives me an approximation. An approximation of 1.5563. And there it is right there. So I will switch my highlighter to turquoise. There's 36. 15563 gave me this. All right. So let me go back to my pen and do the log of 2 plus the log of 18. So the log of 2 plus the log of 18 gives me an approximation of 1.5563. Get my highlighter out. 1.5563 was the log of 36. And there you have it. So is there more? Yes, there is. There's one more. Let me get my calculator back. And it's the log of 3 plus the log of 12. Okay, it gave me 1.5563 again. Pen. 1.5563. So switching to my highlighter, that is also, those three are the same. So what can we conclude from this? What do you think is going on here? So A was all by itself, log of 2 and log of 4, and we got 8. Well, how do I get 8 from 2 and 4? 2 times 4 equals 8. And then down here I have 1.0792, which is log of 12. I have a 2, I have a 6. 2 times 6 equals 12. We also got 12 here. Log of 12 is the same as log of 3 plus log of 4. So that means that 3 times 4 equals 12. All right. 6 plus 6. Log of 6 plus log of 6 gave us 1.5563, which is 36. That is equivalent to the log of 36. And 6 times 6 is 36. I'm going to speed up here now. 2 times 18 is 36. And finally, F, 3 times 12 is 36. Okay. Interesting, isn't it? All right, so what are we going to do now? All right, so here's what I would say. If I have the log of 2 plus the log of 4, it equals the log of 8. All right, well, guess what? I'm going to change this now. Let's let x equal 2. Let y equal 4. So now we have the log of 2, which is x, plus the log of 4, which we let equal y. Okay, and that is going to equal the log of x times y. Interesting. So when we go from addition, if we have addition of 2 logs, we multiply. Okay. All right, page 3 brings us to problem number 3. And it says, what patterns can you see in exercise 2 in the table from exercise 1? Write them using logarithmic notation. Well, I've already done that because I was just so excited that this formula or this property came about. It just is mind-blowing. So I kind of got ahead of myself there. So we see that the log of 3 plus the log of 12 is approximately 1.5664, which is approximately log 36. That's just one of the examples. Number 4 says, what pattern would you expect to find for log of x squared? Make a conjecture and test it to see whether or not it appears to be valid. All right, so x squared. Well, what does squaring something mean? It means taking something times itself. So the log of x squared would be the same as log of x times x. So working backwards, that should equal the log of x plus the log of x. So let's test our conjecture. The log of, let's put this over here, the log of, that looks like 10g, let me rewrite that. The log of, pick a perfect square, 9, equals the log of 9, or if this is an x squared, this would be 3 times 3, which equals the log of 3 plus the log of 3. So now let me get my calculator and test our conjecture. So log 9, enter. Log 3 plus log 3. Whoa. All right, it worked. Okay, so let me get this out of the way. And let's put it into neater words. So I would expect that log of x squared equals log of x plus log of x, which equals 2 log x. They're showing it that way. Interesting. This is verified by the fact that log of 4, they're using 4 for an example, is approximately 2 times log 2. Log of 9 is approximately 2 log 3. Well, log 3 plus log 3 is 2 log 3. So if I bring my calculator back up and if I do it that way, 2 log 3, that's the same as log 3 plus log 3. That's log 3 times 2. You get the same number, okay? So what they're actually doing here now is giving us a new property here. Where did the power go? Log x squared equals log x plus log x, which equals 2 log x. So the 2 went from the power out in front. Number 5. Number 5 says to make a conjecture. Move that there. For a logarithm of the form of log of x, y, z, where x, y, and z are positive real numbers. Provide evidence that your conjecture is valid. So I am going to just do this. So I'd say it appears that log of x, y, z would equal log of x plus log of y plus log of z. And this is due to applying the property from exercise 3 twice. So log of x, y, z is equal to log x, y, and then they just put a dot z just to separate them. So then they said that would be log of x, y plus log of z. And then they did log of x plus log of y plus log of z. Or, and here's where this gets interesting, because in Engage New York, they're always giving examples about things. And then it might say, Susie claims that this is this and this and this is. But Bobby says that it's this. Which one is correct? And the reason I'm doing this is because I copied this from the teacher edition. So it says it appears that x, y, z equals log x plus log y plus log z. We can see that log of 18 equals 1.2553, which is approximately 0.3010 plus 0.3010 plus 4771, which equals log of 2 plus log of 2 plus log of 3. Okay, so I want you to focus on this and you tell me where the problem is. Pause the video, see if you can find an error in the solution manual. Log of 18, and they're saying it's this. Log of 20, and they're saying it's this. And log of 36, they're saying is this. Just without even looking at the decimals, there is a problem. All right. So when I look at this, I say, okay, well, 2 times 2 is 4 times 5 is 20. That's okay. 2 times 3 is 6 times 6 is 36. Perfect. Because that's what our property that we just came, what we just came to discovering. But 2 times 2 is 4 times 3 is 12. So which did they mean? So I brought my calculator out and I checked them. So what is the log of 2? The log of 2 is 0.3010. All right. The log of 3 is 0.4771. So these values are correct, but do they add up to 1.25? 0.3 plus 0.3 is 0.9. 0.9 plus 0.4 is 1.3 something. So there's a problem here. So I tried to figure out which one they did wrong. So I tried log 2 plus, it's either 233 or how else can we get 18? 3 times 3 is 9 times 2 is 18. I'm thinking it's 233. So if I do the log of 3 now, plus the log of 3, that is going to give me 1.2552 rounded to 3, which is this. And if I check log 18, that is the answer. So they did a typo here. This should be a 3, and this should be a 0.4771. Okay, all right, anyhow. Now on to example 1. It says use the logarithm table from exercise 1 to approximate the following logarithms. Okay, so I brought the table in. These are logs 1 through 9. We should be able to find these with our new rule. So the log of 14, I need to find two numbers less than 10 that are the product of that. So I'm going to rewrite this as the log of 2 plus the log. Actually, let me write it this way first. The log of 14 can be rewritten as the log of 2 times 7 because 2 times 7 is 14. Agreed? All right. And with our new rule, I can now say that that would be the log of 2 plus the log of 7. So then I'm going to say that, well, that's going to be an approximation of log of 2, 0.3010 plus log of 7, 0.8451. So that is going to be an approximation of 1 plus 0 is 1, 5 plus 1, 6, 4 plus 0, 4, 8 plus 3, 11. Okay, so then if I get my calculator out and check that, log 14, enter 1.1461. Pretty cool stuff. All right, log of 35 equals the log of, how can I represent 35 with two numbers less than 10? What, in other words, what are the factors of 35? 7 times 5, right? 5 times 7 is 35. So that would equal the log of 5 plus the log of 2. So that would be an approximation. Log 5 is 0.6990, and the log of 2 is 0.3010 plus 0.3010. So therefore, the log of 35 is approximately 0 plus 0 is 0. Oops, no decimal there. 0 plus 0 is 0. 1 plus 9 is 10, carry the 1. 1 plus 9 is 10, carry the 1. 6 plus 3 is 9 plus 1 is 10. So that comes out to be 1. Huh. Am I right? Let's check. The log of 35. What did I do wrong? 5 times 2 is 10. No wonder that I got that answer. What? Why did I do this too? My fault. All right. So anyway, that's supposed to be log 7, which is 0.8451. Hopefully you were doing this and saying, dude, you're not doing it right. Hello. 1 plus 0 is 1. 5 plus 9 is 4. Carry the 1. 9 and 4 is 13. 14. Carry the 1. 8 and 6, 14. 15. 1.5441. There it is. Okay. All right. So there's example 1. All right, so page 4 brings us to 2 more examples. So let's continue with this process. The log of 72 is the log. I'm looking for factors less than 10, and it's 9 times 8. So I'm going to put log of 9 times 8, which equals the log of 9 plus the log of 8. Substitute. The log of 9 is approximately 0.9542 plus the log of 8, which is 0.9031. And the log should be the sum. 2 plus 1 is 3. 4 plus 3 is 7. 5 plus 0 is 5. 9 plus 9 is 18. So the log of 72 is approximately 1.8573. Log 72, enter. 1.8573. All right, this is pretty cool. One more. Log of 121 equals, the log of 121 is a perfect square. which is the log of 11 times 11, which equals the log of 11 plus the log of 11. Or we could think of that as this. I'll say, or the log of 11 squared, which equals 2 log 11. All right, either way, we don't have a value that is 11 on our table, so we can't do that without the calculator. So the log of 11 plus the log of 11 is 2.082, and I could do 2 log 11 and get the same answer, or I could do log of 121 and still get the same answer. All right, so we had to use our calculator there because our table only goes up to 9. So this is fine and dandy for numbers that have factors, all factors less than 10. Other than that, we are still required to use a calculator. All right, so exercise 6 through 8. Use your calculator to complete the following table, round the logarithm to 4 decimal places. So here's the table, pause the video, fill this in. When you come back, I will show that what you should have received or gotten from your calculator and put into the table. Okay, so here is what you should have gotten when you put that in the calculator. And notice what's going on there. Log of 2, 0.3010. Log of the reciprocal, 1/2, just negates the answer you got in your calculator. Go down to log 20, 1.3010. 1 over 20, negative 1.3010, and so on and so on. So number 7 says, what patterns can you see in the table from exercise 6? Write a conjecture using logarithmic notation. Okay, so what you should say is for any real number x greater than 0, okay, they have to be positive, the log of 1 over x equals the negative of the log of the original x. Number 8 says to use the definition of logarithm to justify the conjecture you found in exercise 7. So if log of 1 over x equals a for some number a, then 10 to the power of a equals 1 over x. Then 10 to the negative a equals x, and thus log of x equals negative a. So we then have log of 1 over x equals the negative log of x. Okay, so there it is. All right, page 5 brings us to example 2. Okay, so it says to use the logarithm table and the rules we have discovered to estimate the following logarithms to 4 decimal places. The log of 2,100, no calculator. Watch this. The log of 2,100 equals, well, 100 times 21. And what is 100? Well, 100 is 10 squared. So I can write this as the log of 10 squared, which is 100 times 21. Okay, remember our rules. When we have 10 to the power of anything, that anything becomes the number out in front. So that is now going to equal 2 log 21, which is 2 plus, I should say. We're adding it, 2 plus the log of 21. Well, what is 21? 3 times, not point, 3 times 7. Okay, so then I can rewrite that as 2 plus the log of 3 plus the log of 7. So that is going to equal 2 plus the log of 3 is 0.4771 plus the log of 7 is 0.8451. This is going to give us, we have to work from the left, or I'm sorry, from the right to left. 1 plus 1, 2. 5 plus 7, 12, carry the 1. 5 plus 7, 12, carry the 1. 8 plus 1 is 9, 9 and 4 is 13, carry the 1, and we get 3.3222. Just going to check this just in case. And there it is. The log of 2,100 is 3.3222. All right. So that being said, now let me do the next one. All right, part B from example 2. This one, the decimal got moved the other way. So 1, 2, 3, 4, 5 decimal places. So this is going to equal the log of 10 to the negative 5 times 49. Well, what is 49? Let's just leave it as 49 for right now. 49. This is then going to equal negative 5 plus 49 is 7 squared. So that is going to become negative 5 plus 7, just kidding, 2 log 7. So then that is going to equal negative 5 plus 2 times 0.8451, the log of 7. Okay. So that's going to become negative 5 plus 2 times 1, 2, 2 times 5, 10, 2 times 4, 8, and 1 is 9, 2 times 8, 16. Okay. So I want negative 5 plus 1.6902. So that is going to equal a negative 3 point. I'm not taking a total of 2 away. I need to find what this would get me to 1. So this would be 8. This would be 0, 1, 3. Is that right? No. No. Think of 9, 9, 9, 10. 9 minus 0 is 9. 9 minus 9, 0. 9 minus 6, 3. There we go. That's better. Negative 3.3098. All right. And let's check it. The log of 0.12349. Enter. Negative 3.3098. Ooh, okay. Next one. Okay, so here we go. Here's the next one. Log of 42, 42 million. Okay, so I'm going to rewrite this as, well, how many zeros is that? 1, 2, 3, 4, 5. That's 45 times 10 to the 5th. So that's going to equal the log of 10 to the 5th power times 42. So by our rule, that power goes out in front. It's 5 plus the log of 42. Okay, which is going to equal 5 plus the log of, okay, now I want two numbers that are factors of 42 that are between 1 and 9, or between 0 and 10, I should say. So 7 times 6 is 42. Okay, so 6 times 7. All right. So then we're just going to substitute in now. Equals the log of 5 plus the log of 6 plus the log of 7. So that is going to equal 5 plus the log of 6 is 0.7782 plus the log of 7, which is 0.8451. So this is going to equal 2 plus 1, 3, 8 plus 5, 13. 7 plus 4, 11, and 1 is 12. Carry the 1. 8, 9, and 7 is 16. Carry the 1 will make that 5 a 6. And I'm using an equal sign here. And wherever I switch from the word log to a decimal, I should say approximately. Same with here, same with here, same with here. Wherever I switch it to a decimal, I'm being really sloppy here. I need to say approximately. So the answer should be approximately 6.6233. Let's check it. The log of 42, 1, 2, 3, 4, 5, 6 million is 7.6233. Whoops, there's 6 zeros. Glad I checked it. Not 10 to the 5th, 10 to the 6th. Hopefully you had this and were saying to the computer screen while I was doing this that I was making a mistake, but I didn't hear you. All right, oops, now that's 7 because I carried a 1. All right, so it's 7.6233. Next one, D. Okay, so got this all set up now. Let's do log of 1 over 640. Remember the rule. That is going to equal the negative log of its reciprocal, 640. Okay, which is going to equal the negative log of 10 times 64. Okay, so the 10 to the 1 goes away, or it's a 1, 10, think of that as 10 to the 1. That is going to equal negative 1 plus, okay, the negative power, and then log of 64, which I'll just write it for this time, 64. So that's going to be the negative 1 plus the log of, and 64 is 8 squared. So that's going to equal negative 1 plus 2 log 8. Okay, I'm bringing that 2 out in front, or you could have said that's 8 times 8, so it would be log 8 plus log 8, but log 8 plus log 8 is 2 log 8. All right, so I like doing it this way because I'm now familiarizing you with the power rule of logs at the same time. So negative 1 plus 2, and the log of 8 is 0.9542. Okay, that is going to equal negative 1 plus 2 times 2, 4, 2 times 4, 8, 2 times 5, 10, carry the 1, 2 times 9, 18, and 1 is 19. So it's negative 1 plus 1.9084. Did I do that right? No. The whole thing's negative, right? So when I do this, I should have a negative sign outside. So this would now become negative 1 minus when I distribute. Okay, I need to be more careful here. So a negative 1 times the total inside would become negative 1 times a negative log, which is negative 1 minus 2 log minus. Okay, all right. Okay, made another mistake. I have 9 written down. All right. 9031 is the log of 8. 9031. Multiply that by 2, I get a 2608. Negative 1 minus 1.8062 becomes negative 2.8062. Check with my calculator, and I say the log of 1 divided by 640 gives me negative 2.8062. Okay, sorry about those little errors there. Okay, so page 6 brings us to the end of lesson 11, which is the most important property of base 10 logarithms. So review this lesson summary and go to your problem set.